Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In last section, we discussed about the design of plain beam and pedestal for a steel column, steel structure having steel columns. So we had modeled a separate foundation model to design the plain beam and the pedestal, and those plain beams and pedestals are detailed as per IS 13920. So as promised in last section, I told that in this section we shall design the foundations. So before we go to the foundation, let us have a look in the original STAAD file of the building. This is our original STAAD file of the superstructure. We can say superstructure. So you can see the movement is these are fixed base. They are fixed in one direction. So we have to take into consideration that direction. If you see, it is fixed about this direction. These columns are fixed about this direction. You can say similarly these columns. So we have to keep in mind the direction of the fixity while designing the footing in order to arrive at economic footing design, economic foundation design. So for this column, we shall design isolated footing. Let us go back to the substructure model, that is foundation model. So this is our foundation model. So we have to arrive at a dimension. We have to take take the reactions. So these were our columns in which the columns of the superstructures were fixed in one direction, and this is the column where the columns on the superstructure was pinned. So for this column we shall have a square footing, because here mostly the axial load will be critical, and movement in the footing will be just because of the horizontal forces transferred from the shear of the steel column. And for these columns there will be additional movement in addition to the movement transferred by the steel column above. Additional movement because of this horizontal force. You can say this horizontal force will be there. There will be horizontal force in this direction also, but about these directions the columns on the superstructures are not fixed, they are released. So along these directions much of the movement will not be created. So we will have rectangular footings for columns which are fixed in one direction. So let us now take the reactions. We will have two cases, one for lateral and one for gravity load. So let us first cut the section at the foundation. This is node number 51. Tool, cut section, exit plane 51. So we have this. So go to mode post processing. So select the node, select all the nodes. Report, support reaction. So we have to take the loading off. These are the foundation load case combination which are created. One DL plus one LL, one wall is also a part of dead load, and then one line. So we will take this reaction. Note that for design of foundation, we have to always consider load factor of 1. So foundation size is being decided on the basis of load factor 1. So this is our load case for gravity load. So we shall paste this on Excel file and let us wrap this, format cell, alignment, wrap text. So now next case will be our lateral cases. So again select all the nodes, report, support reaction, loading. So from 51 to 606, these are all lateral load cases which involve both earthquake and wind load cases. So this is our lateral load cases. So now let us assume a footing size. L, B. Now section modulus of footing. Section modulus of footing. Along length, and then section of modulus footing along breadth. So this is equal to 1/6 B L square. You can see, and along B it will be 1/6 L B square. So what is this? This is nothing but, suppose we have a rectangular footing like this. We have a rectangular footing like this. Now this is the major axis. So moment of inertia about major axis is moment of inertia about major axis is equal to B L Q divided by 12. So BL cube. Now we know M by I is equal to M by I is equal to L by Y. So basically, so M is equal to I by Y into F. F is usually the permissible stresses. So this I by Y is called section modulus. So what will be? So this is BL cube superscript. So what is the maximum distance of the extreme fiber? This is equal to L by 2. So our section modulus Z is equal to I by Y is equal to BL cube by 12. Then this is B divided by L by 2, which will give us L by 2, which will give us section modulus about major axis. So section modulus about minor axis can be also worked out in similar manner. So format cell. Superscript. Now we have decided we will have square footing for node number shift N, node number shift S, so shift K will show the node. Node number 52 will have square footing, and rest of all other footing will have rectangle. So let us separate node number 52 from this. So let us keep it somewhere here, and then again here in the lateral load cases. Let us go to node number 52. This will have square footing. So I have cut it and paste it here. So let us delete all these rows. Delete. Now to have a initial footing sizing, we will first consider a square footing, and later while designing we will change them to rectangular footing, so that we know which size will be best economical. So let us first take one by one. So the pressure is equal to P by A plus M excess by Z excess and M so for STAAD we will have this as this is our Z axis, so MZZ by ZZZ, so MZZ by ZZZ, then M excess by Z excess. So you can see for this so this is our Z axis and this is our X axis. So section movement about Z axis will control by major axis. So let us now, what is from the soil investigation report, we have to take the safe bearing capacity. So safe bearing capacity, let us say 10 ton per meter square, 10 ton per meter square, 1 ton per square meter is given in the soil investigation. We have to refer to the soil investigation report to have the soil recommended soil bearing capacity from the soil investigation consultant. So this is usually net safe bearing capacity which is given. Otherwise we can arrive at gross bearing capacity is given in the soil report, then we can arrive at net safe bearing capacity by deducting gamma d. There is gamma is the density of the soil and d is the depth of the foundation. So this 100 ton per meter square is equal to 100 kilonewton per square meter. Now, since for this building we will have a grade slab at the plinth level, so we can consider the all the pedestals are tied in each direction. So we can increase net SBC for lateral load. Net SBC for lat load is equal to for 25% increase, assuming medium soil having SPT value more than 10 or around 10. So we need to refer the earthquake code for that. So this will be 125 kilonewton per square meter. So now our this is equal to B L square, and this is again 1/6 into L B square. Both are same. So resultant pressure is pressure. This will be before that we have to compute the area also. So let us take the area also. Area is 1. Area of the footing is 1 into 1. This. So P by A. So pressure is equal to pressure. Pressure is equal to P is our this force Y divided by A area. Then we have to take absolute moment, so that whatever is the direction doesn't matter. So our mz is the moment in the measure direction. So mzz divided by section modulus about measure direction. Then again absolute section modulus about minor direction. So you can cut and paste it here. So you can see the pressure is 463, which is more than 100 kilonewton. So we have to make this like this. F4 will fix the cell, reference cell. So $K, you can see the dollar sign is coming. So now if you pull it, you can see how the pressure is coming. So let us now try with 1.5 by 1.5. So still, so 1.25 by 1.25. Okay. So there are two footing in which 1.25 is working. And let us see this is working for lateral load also. So again here copy, paste. So now we pull it. So let us make condition here. If this is greater than 100, then unsafe. Let us keep the other cell empty. Paste. So all these are unsafe. So let us make it 1.4 by 1.4. This here we have to put a dollar sign again. W3 is F4 dollar sign. So unsafe, pull it again. So you can see for 1.25 and 1.25, you can see two of our footing are safe. These are node number 50 and 48. Now let us see whether they are safe in lateral load case on node number 48 and node number 50. So node number 48. Here also we can put a command like this: copy, paste. But we have to change this one. This should be 125 dollar sign F4. Okay. So let us come to node number 48 and node number 51. Node number 48, it is unsafe. Node number 50 also unsafe. So let us increase it by little, 1.say by 1.35 by 1.35. So node number 48 is totally safe now, and node number 50 is also safe. So now let us put a color to this. Let us take green color, 48 green color, and green color. If you want, you can put a border to this, and node number 50 also green. So let us make a legend also here, somewhere here. Insert F4. So green color is 1.35 by 1.35. So for these nodes, 1.35 by 1.35 size of footing will work. So now let us increase this to say 1.5 by 1.5. Now we see two more, 47 and 49, and 104 has become safe. Copy, paste, copy, This 52 was also safe in 1.35. Let us go back to 1.35 by 1.35, 1.35 by 1.35. So 52 was also safe. Let us check in lateral load also. 52, 52, 52. 52 is unsafe in 1.35. So we remove the color. No fill. So now let us change 1.5 by 1.5 by 1.5. So we have now 47, 49 and 104 safe, and 52 is also safe. 47, 49, 104 or 52. 47, let us see 47. 47 is unsafe. So let us increase it bit. 1.6 by 1.6. Now 47 is safe. Next is our 49. Let us go to 49. 49 is unsafe. So let us increase it little bit. 1.65 by 1.65. So 48, 49, 49 is still unsafe. So let us make it 1.75 by 1.75. So 49 has now become safe. So next is our 51 and 104. 51 and 104 and 52. 51, let us go to 51. 51 is safe. Then 104. 104 is also safe. Then 52 is also safe. So let us put a different color to this footing. 47, say brown color, brown color, brown color, brown color. So 46, 47, 49, 51, 46. 46, brown color. Then our next footing is 47. 47 is also brown color. It is not brown. It is brick color. So 47. Then 49, 51 and 104. 49, 51 and 104. 49, 49, 51, and 104. And then our 52. So let us make a legend here again. .75 by 1.75. Now let us make the footing size by 2 meter by 2 meter. So they have become same. Let us see in the lateral load case also. they are all safe. So let us make it a different color, say blue color. So this is 2 meter by 0.0 meter. So this will be our blue color. So now we have arrived at 3 types of footing. Maybe at the time of design we can still further change the dimension to have similar type of footing for this 4 column 1, 2, 3, 4, because this will have almost similar kind of movement, although not the axial loads. So it is up to the designer. So these are our footing. So we have for 48. So these are, let us note the node numbers. Size, L, B, node number. So green is 48 and 50, and brick color is 46, 47, 46, 47, 49, 51 and 104 and 2 meter by 2 meters are 46. Sorry, this is 2 meters 43, 44, 45 and 103. So we have grouped all the footings as per the loadings under various combinations. Now next step is to design the footings for this node. So first we'll take 48 and 50. Let us see which are these nodes. And 50. These are the 2 nodes. This is one of the Excel file which I had prepared for design of isolated footing. So before taking up the actual design, I must explain this Excel sheet a little bit. So you can see the footing sizes, pedestal sizes, everything is being given. So we have to paste the gravity load cases of the chosen node here below, and we have to paste the lateral load cases. There is the uplift case. So we'll fill each of them. Now one more things. In gravity load cases, this is the detailed design. This is the design of tapered footing. The load factor is taken as 1.5. So whatever bending moment we are getting because of the soil pressure below of the footing, we have to bending moment and shear force we are getting, we have to multiply this by load factor of 1.5 to get limited strength of design force. So one more thing, in this case, in this detail sheet, I have taken structures of the footing on one side, that is because the plinth level is about at certain always at certain height from the natural ground level. So for the adjustment, mostly for there are many columns which are adjacent column in which there will be footings will be on there will be structures on single side only. So we should consider that as well. In lateral load case design, you can see I have taken the lateral load factor for 1.2. So whatever pressure we are getting below the footing because of a load factor of on, we have to multiply the bending moment and shear force obtained from that by 1.2 because this is the lateral load case. So here we are not considering 0.9 into 1.5 because our load, all the footing load cases have load factors of on 1 only. So let us now this is our foundation model. This is node number 48 and 50. Go to post processing report support reaction. First we have to take the gravity load case. Okay, let us paste it. Paste, and then we have to take the lateral load cases also. Report support reaction loading. On to 2016, 6016 5051 to 6016 the lateral load cases. So we are taking this, copy, and then paste here in the lateral load cases. You can prepare this Excel sheet by yourself by referring to some book. If you want this Excel sheet, you can write to the following email. I will happily share this Excel sheet, but I will advise that you prepare the Excel sheet of your own by having an idea by going through this Excel sheet. So you can write to this email. You can write to me to at strengthrealization@gmail.com. I will be happily share this Excel sheet with you, and you can go through the Excel sheet and how the design is being carried out. So you must understand, refer to the textbook to understand whatever is being done. There could be a issue of linking. So that is why I suggest you prepare your own Excel sheet, because then only you will know what is being happening in the Excel sheet. So let us come back to the problem again. For this footing, we have taken 1.35 by 1.35 as the size of the footing. Greater thickness of the footing, let us take 0.35, and lesser thickness of the footing 0.5. We shall provide an offset of 0.075 around all the footings. Depth of the footing below 1.5 meter. Our column length is, so we have to, this spreadsheet is made with respect to the x direction as measure direction. So we have to, our pedestal sizes were 0.75 by 0.653. So let us take it 0.75 meter length and 0.653. You have to be careful while putting the which is the length in this Excel sheet, which is the weight in the Excel sheet with respect to the STAAD file. So otherwise it could produce uneconomic design of footing. So let us consider the plinth level as 450 mm above the natural ground level. Density of the soil, let us take it as 18. It has to be taken from the soil report. So type of the soil, let us take it 30 degree. We can take it, this also we can refer to the soil report and get the value, the soil angle. Now, this is basically soil angle of friction. The type of the soil is coarse grain soil we have taken. So this we can refer to the soil report and find whether which type of soil is there. Still free, three type of soil is there given. These values are taken from the soil book of Professor Korean of IIT Delhi. So now we can see these are 1.35 by 1.35. Okay. So 22 kilonewton of extra load is there on the above the footing. So you can see this is the critical load. Now here also this is the critical load. Now let us try to economize this footing size. So let us 1.35 by 1.35, 1.35 into 1.35, into 1.35. So if we take one side as 2 meter, 1.8 as 1.5 meter, so other side should do with 1.2 meter. 1.2 meter. Before that, we have to put the other values as well. See, the depth of the footing is below 1.5 meter, 1.5 meter depth of the footing. So allowable bearing capacity we have taken is 10 ton per meter square, 10 ton per meter square. So this should become net bearing capacity as 1.5 meter. Net bearing capacity 1.5 meter. So this is equal to 10. So gross bearing capacity, gamma D has been available. Gross bearing capacity for lateral load, this is net bearing, increasing net bearing capacity, then plus gamma D. So now with 1.35 and 1.35, our maximum pressure in gravity load cases works out to be 67.46, and let us change the dimension as we have discussed. So 1.5 by 1.2, still remains same. So power now let us check with lateral load cases 127.72 is maximum pressure because of lateral, and allowable is 152. So our size is okay, and we can reduce this bit and see. Let us make it 1.4 by 1.0. That is 1.1. Okay. 1.1. Let us check it. It is 149. 152 is the maximum lateral load, so it is safe in lateral load. Now our critical load case is this. So let us mark it red, and then in lateral load cases our critical load is this. Let us mark it red. This is 48. Now we have to link this here, the red one, 50. Under lateral load cases, this node number 48 is the critical one. So this is our bar diameter. Initially we are taking 200 center to center. These are actually linked from the first sheet. So you can change it, but you must remember whatever you are changing here, because it is the link will be then disturbed. So we can go sub. Because of one side, it is still safe. Now spacing of bar required, bar required is 430 mm, 200 mm. So our footing is safe. Our footing is safe in both the directions. Then check against overturning. These are also then check against sliding. Then go to lateral load cases. So everything is safe. So this is how the footings are to say that this is F1 footing. For other footing you can term as F2 and then F3, F3. So this is how we should proceed. So we can change the values in the Excel sheet. Here there is not much because 0.35 is very less and 0.2, but still you can, for checking sake, you can try and see what is happening. Let us make it 0.15 and let us make it 0.2. So the footing is safe. We can, but see, usually 200 mm is edge distance always kept. Okay, so we can make it 0.2 and 0.3, and at least to have a bare minimum slope, we should keep it 0.35. see the lateral load cases. If you go to the Excel, everything is okay. Now let us consider we change the dimension, reverse the dimension of the footing. So let us make this is 1.4 by 1. So one point two by 1, it was 1.2, it was 1.4 by 1.2. So with this, the maximum pressure in lateral load cases is 139. 1.4 and 1.1 best ox for this case. So now let us see what happens to the lateral load. So it is 149, which is less than 152 kN per square meter. So see best optimized solution. Now let us reverse this dimension, or let us see what happens when we reverse this dimension. 1.1 into 1.4. Now see what has happened. The absolute maximum pressure has exceeded the gross allowable pressure under lateral load. So that is why we should have footing, length of the footing in the direction in which greater movement is acting. For mostly the adjacent columns which are fixed in one direction, this should work. And for the interior column and corner columns, mostly the square type of footing best works. For interior column, it could be either square footing or rectangular footing. With this tutorial on design of a steel structure with STAAD Pro completes. I hope I have been able to provide a complete solution for a building. And if this complete this series, I'll come back to you soon with a PUV building. Initially, I will start with a building having crane in a single way. Then I'll extend it to multiple way, having crane multiple way, and then in third case I will have crane running, simultaneous crane running on the crane girder. So please keep watching my videos. I'm sure if you keep watching my videos, YouTube channels, so you will be ahead of many structural engineers who just want to know how to design but do not know why to design. What is the basic behind the design? So whenever the new problems come, they are not able to attend to that problem because they do not know the basics. So I am trying to brief all the things whichever I have learned in this more than 25 of my years of my work experience and share with you so that you can benefit from my experiences and can keep yourself ahead of other structural engineers. Thank you. Thanks for watching.